When we think of energy, we think of, well, we actually think of the ability to do work. When you have a lot of energy, you can get a lot of stuff done. That's just the way it is. And once you've done a lot of work, maybe you need to recharge with a Snickers bar or something like that to give yourself more energy. So there's a close relationship between work and energy. Multiple kinds of energy out there: electrical energy, zap, or we can also have nuclear energy. This is a diagram of a neutron entering a big old atom and causing it to split, which gives off a bunch of energy and 3 more neutrons to keep the chain reaction going. Chemical energy, that's where elements or compounds combine in some way or break apart in some way. When you light a match, the fuel on the tip of the match combines with the oxygen in the atmosphere to create a flame and also create thermal energy. Yeah, heat. That's a form of energy as well. Mechanical energy would be like machines or pushing something. And that's kind of where our focus is going to be right now. But there are multiple different ways of describing energy. When we talk about energy, however, there are really 2 big categories. One of them is called kinetic energy. That's the energy of motion. A ball that's moving has more energy than a ball that's just sitting there. It has more ability to do work, especially when it hits something. But there's also something called potential energy, which is the energy of position. If you take a spring and compress it, it's in a different position than when it's relaxed, and it has more potential energy. Or looking at this picture, we have bricks here. The ones that are down low close to the ground have low potential energy because if you drop them, they don't go very far and they don't do much work. The bricks up here have more potential energy. The bricks up here have the most. That one in particular right there has a lot of potential energy. How did they get potential energy? Because this dude right here did work to lift those bricks up higher and raise their potential energy. That's the connection, work and energy. Now, what about this brick right here? Well, it has potential energy because it's way up above the ground. And by the way, deciding how much potential energy something has kind of depends on where you decide 0 is, and I chose the ground. But because it's also falling, it has kinetic energy. So it has both kinetic energy and potential energy. It has the ability to do work, as this gentleman down here casually reading his newspaper is about to find out. Energy can transform from one kind into the other. As the brick slides off the board and starts to fall, it gets less and less potential energy as it gets closer to the ground, but more and more kinetic energy as it speeds up. And so the potential energy is transforming into the kinetic energy. Make sense? And of course, when the gentleman over here is lifting the bricks up, he's transforming the chemical energy in his food into the potential energy of the brick. Sweet, huh? Before we can have any reasonable discussion of energy, then we have to describe, what does work really mean? We all think we know what it means, but in physics, it's, as usual, very much more specific. Work occurs when a force acts and movement happens parallel to the force. That is, work happens when you get something done by applying a force. That is, movement in the direction of the force. So for example, this gentleman right here is working very hard and exerting a force in that direction. If the car has a displacement in that direction, then the fellow is doing work. If the car, on the other hand, has its brakes locked and isn't moving at all, then he's actually not doing any work. He's not accomplishing anything. Let me rephrase that. He's not doing any work on the car. He might be doing some work on the molecules internal to his body, but he's not doing any work on the car if it's not moving. Weird thing is, if the car is moving backwards, that away, he actually could be doing negative work because maybe he's slowing the car down. So that's the connection between work and energy. What about the chicken and its harness? Now there's a term you probably haven't heard much before, a chicken harness. This chicken is exerting a force this way. Okay, so how can we say that the chicken's doing work if the egg crate is moving this way? Well, the answer has to do with the fact that force is a vector and can be resolved into components. You see, there's a component of the force this way, Maybe we'll call that F sub x because we like x being the horizontal direction. And there's a force component exerted this way. The sum of those two force components, and remember you would add the arrowhead to endpoint by taking this one and moving it over here. The sum of those two force components gives us the original force, but only this part is actually doing any work because the crate is moving to the left, the same direction that the x component is moving. What about this force? Well, it's being exerted perpendicular to the direction of motion, so it's actually not doing any work. When the force and the displacement are perpendicular, no work occurs. Got that? Okay, try to remember that. Force does work only if movement occurs in the direction of the force. As long as you have that straight, you'll be fine in this section. So, what about the math of it? Well, if we have a force that's exactly parallel to the direction of motion, does it make sense to you that if you apply more force, you can do more work? Sure. How about if you apply the force over a bigger distance, you do more work? Sure. How do we put that all into an equation? Well, it's simple. It's just work is equal to force times displacement, as long as they're parallel to each other. That's important enough to put in a little box there. So when the force increases, so does the work. When the displacement increases, so does the work. Couldn't be much simpler. But what about the chicken situation? What if the force is exerted at some angle? In this case, an angle above the horizontal? Well, only this component right here is going to do any work. Remember, there will be another component, maybe pointed that way. Not maybe, it is pointed that way. This component does no work, but this one does. How do we calculate this component? Well, thinking of it as a right triangle here, we can calculate this by using the cosine of the angle. And so if we talk about F times the cosine of theta, that is the horizontal component of the force. That's the component of the force that's parallel to the displacement. And that's what you would multiply by the displacement to get the work. And so that yields this extremely important formula. If that angle happens to be 0, meaning if the force is actually parallel to the displacement, like up here, well, the cosine of 0 is 1, so this formula just turns into this formula. So essentially, this is really the only one that we need. It works in both situations. So the unit of work then is going to be force is in newtons, displacement is in meters in the SI system, and the cosine of an angle doesn't have a unit. So the unit of work is the Newton meter. That is given the name Joule in honor of the scientist James Joule, who studied work many, many years ago, back in the 19th century. That's the SI unit. If we were working in the English system of units, the unit of displacement would be the foot, and the unit of force would be the pound. And so the unit of work would be the pound foot. Typically, we don't use that very much here in physics land. So then what does work do? Well, work can change the energy of an object. Think of it this way. If we're pulling horizontally here, the object might be speeding up, and so its kinetic energy is changing. Okay? Or if we push in the other direction, the object can be slowing down. So again, we change its kinetic energy. Or if we're doing work by pulling upward on something and it actually, in fact, does rise, like the bricks in the earlier picture, we're changing the potential energy of the object. So we can change the energy of an object. That is, we can change its ability to do work by doing work on it. Going back to the example of a spring, if you take a relaxed spring and then apply some force to it to do work on it, well, it only does work if you actually cause it to move. If it compresses the spring, you have now given the spring potential energy by doing work. And that's it. We understand the basic idea of work, and so we're ready to do our example and be done. So here's our example. A lawnmower handle is at 60 degrees from the vertical and is pushed with 5 newtons of force. If the mower moves 22 meters along the ground, how much work was done by the operator, the guy pushing the handle? You might think, well, we've got a formula, just plug the numbers in. But let's be a little bit careful here because I was a little bit tricky in my phrasing. So if we sketch a little diagram, here's our lawnmower. Okay, and here's the force. Now I said 60 degrees from vertical. So that means it's going to be looking like this. Okay, so there's our force, which is 45 newtons. But if this is a 60-degree angle, then this is a 30-degree angle. And that's the angle between the direction of the force and the direction that the lawnmower is moving, the displacement. That's the angle that we have to use. So you have to be careful about this. So using our formula then, work would be force, 45, times displacement, 22, times the cosine of the angle between them, 30 degrees. And you know what? I think I'm going to trust you folks to go ahead and do the computation there. I would advise you to check your calculator and make sure that it's in degree mode and not radian mode. And that's it. One last thing. Let's take a look back here at the formula. Don't forget that when you have a formula with 3 variables, or in this case 4 variables, as long as you know all the variables but one, you can always solve for the remaining variable. So if you're given the work and the force and the displacement, you can find the angle. If you're given the displacement, the angle, and the work, you can find the force. Next time around, we'll talk a little bit more about energy. See you then.